In today's video, we'll explore a mathematical structure called trees, or more specifically, plane-rooted trees, and I will show you that they are closely related to a famous sequence called Catalan numbers, and I will derive it using an interesting piece of math, namely continued fraction. But first, let me introduce some terminology and show that you can interpret and view these trees in different ways. You can imagine them as a modified family tree where in each generation the children are sorted, for example by age. But of course, it's not the only way to see them. For example, a node or a vertex doesn't have to be a person. It could be an outcome or an algorithm. And the edges could represent some if statements or a decision. And the nodes that are at the top bottom, or the people that don't have children yet, are called leaves. The most important feature of this kind of trees is that the order does matter. So the left tree and the right tree are different. But if we don't care about the order, we slightly change the name and just call them rooted trees without the plane. But these are the topic for a different video. In this video, we only focus on the plane rooted trees. Notice that there is exactly only one tree which endpoint that doesn't have any grandchildren. If a tree has no children, its height is 0. If a tree has children but no grandchildren, its height is 1. If a tree has grandchildren but no great-grandchildren, its height is 2, and so on. You can simplify infinite polynomials like this to a finite fraction if they correspond to a geometric series, something that many of you probably have seen before. Now let's take a function whose constant term is 0 and let's substitute it into a geometric series like this and then multiply each bracket out. By using the distributive property, collect all terms with the same exponents. Notice that in each bracket the subscripts add to the same number. Now, surprise, surprise, the number of terms in each bracket corresponds to the number of trees which height at most 2. And to see that this is the case, I drew a picture where you can see that the coefficients correspond to the number of nodes in each branch and that the order in which you multiply these coefficients out corresponds to the order in which the branches are rearranged. And don't worry if you haven't understood everything, cause I have some more examples to show. This time listing all the trees which end nodes and height at most 3. And now using the new coefficients b's that correspond to the number of trees which height at most 2. And now using the same technique as before, where the subscript of the coefficients tells how many vertices there are in each branch and the order in which these coefficients were multiplied correspond to the order in which these branches were rearranged. Notice that now a single product of coefficients doesn't necessarily correspond to a single tree, because the coefficients have changed. They are not all equal to 1 like before. But the procedure has not changed. We still multiply the coefficients through all possible subscripts in all possible arrangements, and that is equivalent to substituting the function with these coefficients that you can see in the top left corner into a geometric series that is multiplied by x in the numerator because of the additional root node that connects all the branches and because I count the trees by the number of vertices and not edges. By repeating this procedure and by updating the coefficients in between, we get a recurrence for the number of trees with height at most n plus 1 using the function for trees with height at most n. If you let n go to infinity, we get all possible trees with all possible heights and also get an infinite continued fraction which repeats itself in the denominator. This can be used to simplify that equation into a functional equation that can be solved by treating the function as a variable t and the variable x as a constant. And using the quadratic formula, we get two solutions, and the solution with a minus is the function whose series expansion gives the Catalan numbers. These numbers appear in many different problems and can be derived in many ways, but this way is a less known one and also my favorite one. That's why I wanted to share this video with you, and I hope you enjoy it and have a good day.